Hi, this is Bill Foote, and welcome to System Dynamics 101. This is the second course in a multi-course series in which we apply Bayesian learning techniques to strategic decision making and attempt to take it into the realm of an artificial intelligence eventually, where that's almost an oxymoron. We will discuss that in future. But the idea of intelligence is to be able to look at data, form ideas about the data, verify those formed ideas in the data, and then move on perhaps to use what is consistent with those ideas in the data, consistent to make good enough decisions, and then repeat the process. That's a very wide swath and broadly painted approach uh, to the theory of mind involved in decision making, which is quite old, many millennia, and sources of it seemingly can be found in places like Aristotle and a little bit of Plato and certainly Aquinas and Thomas and others as we go forward. And we're going to be taking that Aristotelian bent for sure. We will not believe that we have preconceived notions coming out of nowhere. We do believe that uh, as we go forward here, that the mind does form ideas about what it sees, perceives, observes, otherwise deals with um, outside the mind, which could be in your body too, and with other bodies and their minds. So interesting, complicated thing we're looking at here, and thus system dynamics. And we're looking at this over time. This week, we're building on week one's predator prey model. It's basically an interaction model. Predators, maybe, prey, maybe, especially for thinking of biological organisms, Canadian lynx and snowshoe hares is the original one. We could be thinking of a new technology that uses a lot of energy but makes quite a bit more available, but that energy actually dissipates the technology, it blows it out. Thermal resistivity, for example, which is something that happens in iPhones and lithium ion batteries. So this could be just that, those sorts of interactions. There's also collaborative interactions, highly non-distributive, which means that value can actually be created in the interaction. There's something new there in the interaction. It is not just a balancing of existing interests. So that's another thing to think about as we go forward. And in all of this, we're going to apply Bayesian updating rules, a probabilistic approach to learning, something that is actually deeply embedded and very much inside of most artificial intelligence approaches, including those that use self attention as a metric to decide what tokens you're going to see in ChatGPT or not. It's the same kind of thinking, perhaps different technological representation. As we go forward here, there's playlists. Here we are in Add Inference. Playlists, there's Zoom calls every Saturday. And if you ever want to get in touch with me, just holler and we can arrange a time to talk. So this week we're limiting the model. We're putting constraints on the model, and those constraints are capacity and availability of interactions. And this goes back to the limits of growth system archetype, which we can investigate and have investigated in the first course, which were the basics of system dynamics. The week two notes are interesting. Yeah, this is all just drawing it out. Okay, a little bit messy, not very pretty. We'll let Vincent make the nice drawings. but it's a 6-step process. We ask questions. What happens when we put capacity inside the model? What happens when we endogenize uh, several things within the model, like rates of acquisition and switching in the model among the different actors, um, deposits and withdrawals if it was a bank, redemptions if it's a fund, those sorts of ideas. And here we're going to introduce a customer base that will be applied to the two interacting customer bases. So this will be the potential market. And those sorts of questions will come up with some sort of loop diagram where we would have a discussion around how these different entities, namely potential customer base and then the two differential Mooseco and Wolfco customer bases, might interact. And then somehow we're going to have to come up with an allocation rule. We call it phi or phi, depending on what English university you might have gone to. With the Greek, I like the Greek just because it's so different than everything else, because it's a tough rule to figure out. This is going to be an allocation rule. How do we allocate to the moose and allocate potential customers to wolves initially? And then as we proceed in the simulation, this is the problem with this. And we just choose a very simple ratio rule. So moose over moose plus wolf, 1 minus that will be down here, and then some sort of availability function. Don't absolutely need this, but we will be using this. It helps to smooth some of the wrinkles inside of our model. Notice we're only looking at customers leaking out of the customer base in the potential market, either into Mooseco and Wolf. And then this potential customer base really is relying upon decision makers in Mooseco and Wolfco for whether they will want to accept the conditions of being a Mooseco customer or a Wolfco customer. You can think of customer loyalty here. But we have a birth-death process here, as it's often called, acquisition switching. And this part of the model is something that we've already seen, but what we're doing is we're endogenizing the Mooseco rates. The Wolfco rates in and out, we're endogenizing it, except for this one, the switching rate out. Okay. And we can endogenize that as well. That means bring it within the model, no further specification than very, very, very basic rates. Okay, and we could do that here as well, but we're going to take endogenization only one step at a time. Okay, and of course we're asking all the questions of the 6-step model. Here's the 4th step, which is an SFD, a system flow diagram. Down here we have the loop, pure loop, just to start the process off. And here we have over in box 5 some ideas about how we think the moose and wolf call interaction might occur, as opposed to what happened last week, where there was no dampening out. But we think that capacity, according to the system archetypes, will dampen the activity and the interaction between wolf and moose. And then we ask the question, do we have a relevant collection of objects? And we have 3 kinds of objects in our inventory. We have the stocks. Those are the accumulating boxes that you see there, C, M, and W. We have the auxiliary variables, which is just about everything else. Anything that's specified, anything initial wolf, initial moose. Okay. Those things are there. We then say, okay, that's nice. If that's all true and reasonable and relevant and sufficient, do we have all of the causal connections that we're literally hypothesizing among all of these pieces. So these are more calculational down here, and these boxes are accumulators. And it's a well-known idea in mathematics that accumulation really is the more important piece. That's called integration. And then changes in accumulation end up being the derivation, the derivative. Okay, so just keep those ideas in the back of your mind as we go through this video. And the purpose of this video ultimately is to do all of the work that is already in the other videos for this week. But, and here's the but we're going to do it in the spreadsheet. Partly, there's a couple of things in the spreadsheet that I like a little bit better. I've got a little bit more hands-on in the calculation. And I might be able to manipulate things a little bit differently. Okay, spreadsheet thinking is very different from program logic thinking, but it has the same logical structures of what is determined by what other things when in the simulation. And so even looking down here, we have the equations written out in these notes as well. We've got to tighten it up a little bit. We're going to be using some other things called shadow variables in the Vensim model. And the thing I want you to really look at is this iteration of moose and wolves and a new iteration of customer, a potential customer. We have here a model of potential customer with with a disaggregation into wolf and moose, which I think is a little bit more exciting than anything else we've had. I'm often asked, okay, how would you model the potential customer base? Well, there's a lot of other things we could put in here, of course, but the potential customer base has to be relevant to that which it is applied. And we will see this decline. This is a death process, of really being dramatic here. But try this out. You know, try to suss out the equations. This could be a linear programming project over time as well, and it would use very similar relationships. But it's a nonlinear relationship. You can see that we have moose and wolf co-moderating each other in equation 3, and also in equation 2, and also equation 1. And they're co-moderating each other in their interactions. Okay, so these are things that we need to, again, be aware of as we go forward. Fun, huh? Yeah. Those are the week 2 notes. And what I want to look at just very quickly is this note here, which has pretty much everything in it. It has a 6-step with a growth version involved, a 6-step approach, which I am proposing to you is a way to design as comprehensively as possible what it is you're trying to model. Okay, so this is the design, and then the specification steps are usually what parameter values are we going to use, and then we go out and try to build this whole thing. We're doing it in Vensim, we're going to be doing it in R, we're going to be doing it in a spreadsheet. But once you built it, then you go and test it. And that's what the slide bars end up being. You test every little thing. You break the model. You see where it doesn't work, and you see where it does work. And that's very valuable knowledge to the decision maker. Because where it breaks is maybe where the decision maker wanted to go in terms of a parameter value. And then you say, okay, let's see why it's breaking. Comes up with really weird numbers, really weird perturbations in the dynamics and the interactions, and then see if we can model around that to understand it a little bit more deeply, which means another layer of modeling, another Six-step process to get into it a little bit more deeply. This last step is pretty important. Is the design a system? And I continue to look at this because it's really wheeling back up to the very first piece. Is what we're doing relevant to answering the question we're posing? Okay, so relevance. Is it sufficient? Are we including just enough? Are we putting a little bit too much in there that just clouds the discussion? Is are the parameter settings reasonable? I mean, do they line up with stylized facts of what we think the market is? We might be in a situation here where we don't even know what the market is. We're just literally putting the finger in the mouth and putting it up in the air and feeling the draft of wind flowing by. We don't know yet, and that's one reason why we simulate. That's another reason for that. Here's the rest of it. Wolf and Moose, for different parameters, will have these cycles and so on. But here's a very simple model in which, without a potential market in it, which does begin to dampen out. Okay, you can see that dampening here for certain parameter values. And part of the reason for it is we have capacities constraining acquisition in both activities. We could also have capacities or requirements constraining switching as well. That's another aspect that we have to keep so much on hand in stock. Okay, and this takes us through some of the modeling aspects of it. There's a Vensim model. Play with the Vensim model. This time with a input customer, potential customer market base, right? And then show how the equations come out. So this is a documentation of everything that's going on, and we'll have that. But then we get into an R model, and we're going to build the simulation model two different ways. This way is the way that actually it looks inside of the model that we're going to be building and demonstrating for you in a spreadsheet. It's a very simple first order, called an Euler integration. And it's just taking the previous value and adding and subtracting other things from a flows to get the next value of M or W in this particular case. And then you run the simulations and so on. In R, it's a little bit easier to do all of these pieces and then plot them. And we're going to, this is an interesting plot where we're putting one on top of the other with something called a facet wrap in ggplot. We're using Plotly so that we can do this. Okay, Plotly allows for the interaction. A very primitive interaction, but very useful. We sometimes don't need anything more than this. And then we integrate Vensim in R using Jer's and Drod's read SDR, system dynamics in R. Read this model. And we go ahead and make a model in Vensim. It's outputted as an XMILE file. And this is a standardization of data. And then we go through the R, and this is all done in the other videos in more detail. Here we're always building a data frame. DF is a data frame out of this. No scientific notation allowed. And there is our basic 7. There's only 7. And we'll have exactly the same 7, magnificent 7 if you will, in the spreadsheet. We have a solving. The solve does this, where we create a function now, and this means we can iterate this function through different values and create other kinds of simulations on the simulation, take samples of simulated values, which is where we're going to want to go. We're going to want to create some synthetic decision data. That's the idea here, ultimately. Notice we're following the A for auxiliary, F for flow, and S for stock. Here, this is a change, rate of change in the stock for customers, Musco and Wolfco customers, which equations should look very similar to what we have, and we have a return list of all of these things. So R gives us a little bit more flexibility, but we gotta go through the pains of parsing R with our brains and our fingers and making it work. But I think it's well worth the effort. Do this also in Python somehow. And here's a simulation where we plot different simulations of different aspects of the whole thing. This is what we should also expect to see. Okay, here's the bases, potential, Musco. Wolfco goes right down to practically zero. Very interesting. And the moose are left alone, tapping out at about 35. Okay. And it could be 35 million, 35,000. And we do some more work just to feel the differences. These flows are very interesting. Again, these could be interaction flows between investors in a hedge fund who make deposits and make withdrawals. They might redeem their shares. This might be a bank, might be a joint venture. It might be work effort shared across different departments in and out in a project, for example. A lot of ways of thinking about this kind of model. I go through another piece here, which I'm not going to talk about now. I talk about it pretty extensively in one of the other videos, called a fourth order Runge-Kutta approximation technique. Some people say Runge-Kutta, and depending where you are. And it's a very simple modeling approach, which gives you error rates. There's errors in everything because it's an approximation. It gives you rates that are pretty safe. They don't blow up, but there are conditions in which these models can definitely blow up, which means you don't get these nice curves. And you can see that they're all numerically, they look to the naked eye, at least my naked eye, to be continuous. They're not. These are approximations, and there are distances between this. We're just hashing them all together with our brains or with the numerical algorithms we're using. Now, the GPT piece goes through the actual solution based on some, here we're doing a simulation of synthetic data, and then we will do some statistical inference on that simulation using Bayesian techniques. That's coming up. But just want you to be aware that this is what real data looks like, more or less. Okay, so you see the general shape as it goes through a trend, and here you go. But what's interesting about this is, even though it averages out down here, goes up, comes down, and then averages out, there's a lot of possible variation in this particular simulation, whereas the wolves are just going away. Okay, so there's a lot of non-wolf activity going on here, pretty obviously. But again, this is synthetic data. We could have synthesized different data with different parameters, which is something that you ought to do and play with. Right? Play is very important. But if we look at the interaction between the two databases, we see that there's an awful lot of not much going on over here, but a lot of interesting valleys and peaks in the data. And I think those are very important. If this is a physics experiment and this is quantum information among different players, meaning particles like bosons and mesons and fermions and so on, particle physics, this would be interesting that we have these polar regions right here in the data. So there's little dips and rises, and a topographical map is kind of interesting for interpretation. I built also a Flex dashboard app. I don't know if this is going to work. It's been a while since we played with this, which is one of the reasons why we like using R or, there we go, something else. And you can see we built slide bars here. See, there's a reaction going on. Yeah, not much of a reaction over there. We can play with this a little bit. See? Yeah, my data center is apparently, I have the least expensive package on Shiny Apps. But you can see you can begin to play with this, and that's the whole point of building these models, to have this play. It isn't toys. It's playing with it, like think outside of the box. Just let your fingers do some traveling around and see if you can make sense of it. And this is what decision makers do or should be doing with a lot of their models. But that was endogenized capacity. Here's the original model, which we can play with it here. Then the limits, let the poaching begin, and then we endogenize capacity on top of that with a market base. So this one here is you have source code for it, and so on and so forth. This to me is where I can now ask, probably ChatGPT 4.0 right now, build something like this, and it will build it, and not badly. It'll put a lot of it in there. And then if I prompt it correctly, so this whole field of prompt engineering beginning to occur, and it's already been out there for a while outside of my purview at this point, we would be able to get this done very quickly. But it's not different than me having a storehouse, and a perfect memory, by the way, of models that I draw on regularly, and I do, and that's how I can get my modeling done rather expeditiously, because the ChatGPT models might not have the right prompts for whatever reason. And I would love to see a ChatGPT model build the prompts for me now. That's an ask, just to make this efficient. But it's very important for me to know why these things work and don't work too. That's the other side of it. ChatGPT is beginning to, and most good AIs within commercial, government, and other organizations, getting to the why and precisely how and what are exactly the connections. And so when we do engineering, we have a human-machine interface that is very interactive and a lot more efficient and probably more accurate and reliable. That's where we're going with all of this. Mathematicians will always tell me, we write mathematicians write theorems so that you don't have to worry about all the detail underneath, and it works. And you got a formula, so use it. Okay, yes, that's a very simple thing. but this is it's built in something called Flex Dashboard, and I hope this was interesting to you because now let's just go directly to a model. And here's the original model from Vensim, which was this model, where I pulled out with view, copied and pasted all of the 24 specifying formulas. Notice I didn't have any units here. There's a lot of work here, right? That needs to be in here. Um, Documenting. What does this stuff mean? We don't want to lose that knowledge. What does this stuff mean? My preference for a lot of these is this sloppy looking diagram because, well, I can actually get the units and I can get the relationships, and it allows me to play more mind games with this and formulate different conclusions about, in this case, the interactivity of Moose and Wolfco with a potential market now. Okay, that's another aspect. But I took a screenshot of this like I did last time. And I have a Vensim model, different tabs for different tasks, out of which I located parameters. Now it's the same 7 parameters that we saw with the R model. Here's the cut and paste of all of these things. Like I did last time, I just used left, right, length piece to parse this data to get rid of the 0, 1 and spaces and the equal sign, right? So I can get my various parameters. Now notice that a lot of these parameters are here, same ones as before, but except for these. These are new for Moose and also for Wolf. Okay, so those 2 customer bases, but all the rest are pretty much the same. The switching and acquisition pieces and the flows don't have a multiplication times step. That's done internally in Vensim, and we have to remember to do it externally here. And here it is. Same thing as before. Yeah, 12,000 times plus 1. Okay, the 1 is plus 1 is 0. So 12,001 times. And slightly different names than before, a little bit more. Okay, I do not need to conserve space here, but this is roughly a 3 meg file right now, and this is not a complicated model. More complicated models will not fit within, and more realistic models, let's put it that way, will either not fit within Excel very easily, and I only have 12,000 simulation steps here, but I could be going out over several rows. Okay, that's part of the issue. Several columns, rather. Each column is a separate variable in the system itself. Here are the stock variables. And again, use this, it's called the camel approach, I believe, as opposed to the snake approach. Somebody can correct me. F stands for flow, S stands for stock, A stands for, we got a bunch of A's over here. We have a bunch of new A's over here, which are changing. All right, you see that they're mostly changing. One that isn't and it's a problem with this model that somebody should maybe think about when you have nothing else to do, is that the 2 availability indices, do we need them to do the model? No, we don't. But it's something that I was tweaking in my mind about. Here's the amount that we think we have, and therefore what is actually available to the flow. And it's not 100%. You can see that. capacities are always greater than what you can use. And here's the allocation fraction for moose. 1 minus this is the allocation used in wolf. And we can see that we're doing something like this. Now, one of the problems is if this number and, that number depend upon row 3, the current date, this model will go circular, and I believe it will not solve either. Okay, so that's a problem. So a simple way out of it, given the steps are so small, there's no big steps in between. I just use the previous for those, and it wipes away the circularity, the simultaneous equation aspects of some of the rows are affected by this, and it cleared that very nicely and produced the picture that we see pretty much in R and in Vensim. So notice we have O2 now. Availability is coming in. Acquisition rate. And in the switching, that has not changed from before, but the wolf acquisition rate also has O3. Okay, and the wolf switching rate has that. Okay, G2 and so on. And whether I use O3, this really should be Q3, but for whatever reason, and that's something again for somebody to investigate an exercise, why those are exactly the same. If you just work back into the equations, you'll see that they have to be the same. Okay, it's a kind of an equilibrating approach that's built into the model, and that's what endogeneity does. It tends to have an internal equilibration on some parameters that makes the whole thing work, quite literally. And all you do is just write these same equations that are in Vensim, which means you got to go back and forth to the new model. See, that's with availability, and that should have been wolf availability down here. But as I said, those two numbers equilibrate very interestingly. And we might not want them to equilibrate, by the way. Okay. Now the switching rate itself is still exogenous. Everything else seems to be endogenous. And that's interesting in and of itself. So we've not solved the endogeneity problem. We still have some interesting work that we could do. And the graphs come up the same. Okay, the same kind of graph. I'm using a secondary axis here for the potential market to overlay this potential market yellow, dark yellow line. It's almost yellow ochre. It's very, I hope you can see it. I don't know that it's very ADA compliant. It might not be very good. And in which case we need to be a little bit more cautious with our color palettes. So that's something also to think about and work with. We come up with basically the same model. One other interesting thing is if you make all of these integer values, and you can do that using something like this. It takes the floor of each one of these. Okay, and just copy this down and so on. You will come up with a very, very interesting problem. The graph will not look like this. It'll go across and then down and then across again. So this is something that happens when you consider what effectively is a finite field as opposed to a rational field, which has values in between integer values. When you go to a finite integer field, you will find some different solutions. You'll find it more step function wise, and the phasing of the step functions will be interesting in and of itself. It will have different interpretations. But we tend to avoid all of that and pretend everything has another number in between. In fact, life is not like that. We don't have a continuous stream of customers. We don't have a continuous stream of transactions. Machines are turned on and off frequently. All right, so we get different numbers. It isn't a continuum. So we might be a little bit careful about this to bring those thoughts into the interpretation of what we're doing. And with that, somebody I'm following pretty closely right now, there's Michael Penn, has got some interesting videos along with Norman Wildberger on different aspects of how equations like this interact. And it's mathematical, yes, but they're boiling it down so it's intelligible for somebody who's had basic calculus and some basic linear algebra as well, which is behind all of this. All of these solutions can be expressed algebraically. And that kind of knowledge will allow you greater ability to interpret dynamically interacting data, entities, decision makers, components of new architectures and technologies, global geopolitical events, and so on. Is a way of forming how all of these pieces act and interact and where they cannot interact. That's the other aspect of the math. So what I'm going to say now is thank you very much for your kind attention to all of this, and keep following me on this journey that we're on with simulation, with building models, all for the purpose of decision making. And we'll just bring this right back to where we were before. And we always will start with, boy, there's a lot going on this week, isn't there? Should probably just stop the course right here. Paper and pencil. Here's the paper and pencil. All right. Fascinating. And always begin to tell a story, though. And then use these models to help interpret things that the story calls out. That's how we do this. And with that, I'll leave you with add inference, yet another 7 weeks, and here we are in week 2. We're getting deep into it. Pick up Barbara Minto someday. That's a good read for all of us. And some of the readings from the previous week are very useful. Think about these sorts of questions as well. How we prioritize and project and incorporate, okay, different aspects. I'm using the Latin versions from, mostly Cicero, to get a rhetoric, a framework, really. Rhetoric is taking on very bad connotation these days. This is a good connotation. How we can put all of this together into a human decision occurring. Okay. And with that, I will leave you, and this is absolutely a good place to stop for a moment, reflect. Not just stop, now go and reflect and play with the models. And thank you again for your kind attention. See you on the next round.